So yeah, we're the USC Rocket Propulsion Lab. I'm Ryan.
I'm Jayna.
Yeah, I'm the current lead engineer, and
I'm the current lead operations engineer.
yeah, so we're both the graduating seniors, but we're going to tell you a bit about what we've done, and then especially a lot of the work that we plan on doing in the coming years, and actually some work that we're going to be firing in 2 weeks. So, oh, I need to bring my mouse so I can click. Well, yeah, you can see here, these are all pictures of the Aftershock series of rockets. Here's the motor, Shockwave, that was our static fire test. Here's the first flight, Aftershock I, which was a failure, and we can briefly talk about that. And then here's the success of Aftershock II, both in the Black Rock Desert, and this one was out at the RRS Mojave test area. Yeah, so the motor, called Shockwave, was fired in fall of 2023. It had maximum thrust of 3,000, just a little under 4,000 pounds force for, that total impulse. Fired for 16 seconds, and yeah, it was more powerful than our previous motors. I believe it's the most powerful composite case motor that we've ever made, and it's quite a challenge actually. I cut this video off, but there's a bit where it gets a little hot at the forward end. It starts smoking. We mitigated that with extra insulation, etc. Of course, Aftershock II was our flight just this past October. So basically, directly a year after the motor test. Flew to 470,000 feet and basically 1 mile per second at burnout, and that was, the culmination of basically my entire time in college, because when we came in, when we were freshmen, they had a few explosions trying to do a motor like this. I think there were 3 failures in a row. We finally got this figured out and sent it to space, which is what we've been working towards.
Yeah. I guess one of the little known things about one of the things that happened with the Aftershock II launch that I'll talk a little bit into is that it almost didn't happen by just a little bit. At approximately T-minus 20 minutes, it was determined that the avionics unit state was not acceptable. Pretty much nothing on it was working. And this was particularly shocking to us because we had done avionics testing with our unit, a bunch of small tests, dozens, countless of times, and then 2 full avionics rehearsals, really making sure that system worked. And then all of a sudden, it gets on the tower and everything quits.
Was that a hamster?
Yeah, it was hamster that wasn't working. And also a rangefinder system.
And as well as a few commercial systems didn't seem to be picking up their signals as well.
Yeah. So what we decided to do is we decided it's not going to be best for us to launch like this. We're not going to be able to get enough data to prove where we went, to prove what we did. And then also, I don't think we would be able to say that we know our recovery system's going to work with the state of the unit, how it was in. So we halted launch, and the vehicle was deintegrated. And I would point at this event happening as one of the more difficult parts of something that we went to, but also one of the parts that really shows the strength of our team. We were out there in the desert, days, freezing cold. We only had porta potties. Food's not that great out there too. But what we did is our team came together and they looked at the issue, they looked at the unit, and they ended up finding that it was just a small problem with the antenna. They took the antenna out, they replaced it with another one, reintegrated the unit, and then Aftershock II was successfully launched at 11 a.m., just a little bit after that. And then here's some really cool footage of that launch. This was of takeoff. Again, this is at Black Rock Desert. It's going up this time, which is good. That's what we like to see.
Oh, oops.
And then here is footage at just about apogee. You can see our nose cone there, and more importantly, you can see Earth in the background. This was just really incredible for us to be able to see that, we've built this vehicle pretty much from scratch, and then getting it back. And I still remember seeing this footage for the first time of really saying, whoa, that really went to space. It's also been really helpful for us to fight against flat earthers on the internet. Even though they try to push back at us, but we're like, no, we did this ourselves. We know about this.
I will actually say, so flat earthers always ask, well, you must have used a fisheye lens, which this one actually, this specific view does have a bit of a fisheye effect on it. So technically they could get
It
out.
was flat. It's a disc.
They could get at us with this view, but we have another side view that we released. There's a YouTube video that we recently put online, and that there's a side view that looks over the Earth, and that was patently a rectilinear lens, all flat. I've gotten lots of emails about it. Yeah, and Aftershock 1, the thing I mentioned, yeah, another thing, we just keep learning how to be more reliable with avionics. This one did not succeed because of user input on the avionics side. The recovery system was misconfigured so that it accidentally deployed parachutes at liftoff. It's that easy to make a mistake, and it's much more, every year this club learns how to be much more reliable with things, which I'll touch on especially at the end when we're talking about the avionics unit. For reference, this is Traveler 4, the one that flew in 2019 to around 340,000 feet. And I'm showing you this to show what it looked like before and after launch, as well as specifically this shot. That thing got completely shredded up. We tried using carbon phenolic on the leading edges of the fins, and then you can also see this V pattern between each set of fins is kind of like a shockwave effect. There's just shocks coming off the fins, shredding apart the case. For comparison, on Aftershock II, we improved our thermal protection. We added titanium leading edges. Steel could work as well, but it's just heavier. So titanium leading edges, as well as a thermal paint, and it looks, as far as I'm concerned, pristine, the carbon fiber. So that the paint did its job, it came off, took the heat with it, and it's just in a much better state than Traveler 4. The titanium leading edges also turned blue, which we thought was super cool from oxidation in the atmosphere after getting so hot. Kind of like an anodizing process. Yeah, so that's like the basic summary of Aftershock 2. We can answer
What velocities did you reach?
Yeah, so it went
Mach 5.5.
Mach 5.5, and then like 1 mile per second, 5,280 feet per second, and that was around 50,000 feet up when it burned out. Yeah. Yeah, so future work, we are hoping to launch to space as soon as like maybe a year from now. But before then, of course, we want to improve our systems, make everything even more reliable, just make everything work better. So we're going to do that in 2 ways. The first is we're going to improve our propellant, make everything lighter so that we're able to lift more mass to the same height. Aftershock 2, for reference, 470,000 feet is just 20,000 feet below the amateur flight limit by the FAA of 150 kilometers, or more like 490,000 feet. So for the time being, we're going to focus on optimizing our system rather than trying to go higher, because that would be a lot of paperwork. Things we're doing to improve our propellant. We're going with an IPDI curative rather than an MDI curative, which means we have a lot more working time. It's not curing at room temperature. This allows our propellant to be much less viscous and much more pourable. So this is a vacuum chamber we're casting in, and it's essentially just extruding, falling right into the grain. Hopefully, this has resulted again in like a 4.4% increase in grain density. That's like the long-term goal, is using this new formula. We tested it recently. It didn't actually behave as expected. It has more of an industry-like 16% aluminum content. Our previous propellant that flew on Aftershock uses 10% aluminum content, and I think that big jump caused some ignition and behavior problems, efficiency problems that we might need to think about more before we get to using this propellant. Other things we're doing are basically just increasing the quality of our product. Previously, everything's done by hand. It looks kind of like a cake, like you're frosting a cake. However, now we're moving from hand spread liner, or inhibitor we call it, to the inside of the casting tubes, to a much more uniform spread with that device over there. Obviously, backside cracking is the death of a motor. We want to avoid that. Bad propellant will always cause something to explode, so we always want to make our propellant much more reliable. The most important thing we're doing about optimizing the mass, though, is moving to a finical geometry to get a neutral burn profile. Currently we use Bates geometry. There's the grain boundaries, but that means we have a lot of problems with thermal insulation. Roughly 33% of the case mass is insulation, which is ridiculous. That's like, if we can get rid of all of the need for insulation, then we can actually move from 60% mass fraction on our rockets all the way up to 70.
You use aerojet?
No, we use EPDM rubber, yeah. As well as like the standard linen phenolic liners people cast into and stuff like that. So yeah, this new geometry will allow us to achieve the same or a better burn profile without any boundaries between the grains. The propellant will be the best insulator, and that's how we're kind of optimizing our vehicle next.
Yeah, so this is more into the insulation removal that Kraemer was talking about. First of all, you can see here kind of just how much of a hassle generally in our process it is. We have to take our mandrel, stand it up. We take this giant EPDM tube, we're sliding it over. It's a frustrating part of our process, but the more benefits are exactly like what it's doing with our rockets. Seeing a 30% mass reduction, and again, an insane simplification of manufacturing and reduction of case imperfections. One of the parts of using this EPDM is that when we put it along our mandrel, that has a certain thickness on it. And then if we want to eventually do wine layers, or we're putting unis over the entire case length, first what we have to do is we have to build up the thickness of the EPDM on both sides. This takes a ton of time in preparation and cutting these plies out and putting these plies on our mandrel. So it's really simplifying that, allowing us to get cases out quicker. And there are some challenges with this. The first is looking at, before we were able to use the EPDM as kind of a measuring point, right? We have the EPDM here, and then a certain measurement out from this. This is where we need to cut the case on this side. This is where we need to put our pinholes, so on and so forth. We no longer have that, so we're kind of having to refigure out those processes. And also, we're going to be experiencing more heating. We don't have this insulation, and we're not exactly sure how this new propellant is going to behave. We're not sure if without insulation, if it's going to take that, but we're doing testing and we're going to figure it out.
Yeah, theoretically, the new propellant burns a lot hotter than our current one, so we're doing testing on this geometry, on this architecture with our current propellant, which burns less hot. We're very confident that the motor and all this architecture will hold up. It'll mostly serve as getting data on, okay, the case can take this much heat. If we increase the temperature, will it still be able to do that?
Did you say you're using IPDI?
Yes, that's our new curative for the next propellant formula.
Just curious, I've used it, it's super toxic.
Yeah.
I mean, all curatives are bad, but that one's like...
Exactly. So we work at X Quadrum with like professional supervision. All of our students are like doing the work, making the motor, mixing the chemicals. But for safety reasons, yeah, we work with a professional essentially. We have all the proper gear, all that. Yeah. But it is, you're right. we needed to check the right boxes before moving towards that.
And additionally too, just looking at it from a safety measure, our propulsion lead, in order to go and cast our motors, you have to attend a session where you learn about all of the chemicals that we use and what the dangers of them are. And nobody, has to go casting if they choose not to. And then anyone who chooses to go casting does not have to work with any materials or chemicals that they're uncomfortable with. So it is truly also the choice of each individual student.
I was just curious how you might have changed your processes.
Yeah. We looked into it. We purchased all the right gear, and yeah. But of course, the benefits are great. It's a lot more pourable and all that.
Yeah.
So now, kind of separate from that new motor testing, and these are both happening in 2 weeks, by the way. We're going out to the RRS test area and firing both of these, that static fire as well as this, which Jayna can tell you about.
Yeah, so then this is Malibu. This is our rocket that we're flying this spring. And we're doing a few different stuff on here that we'll talk about at some point, but one of the most major parts of this is the fact that we are introducing a payload for this. This rocket serves to test our payload system, to test the recovery system within that. And then we're looking from here, hopefully if this is successful, we're eventually looking to scale this up, to have payloads that we are able to efficiently and reliably send up to space to support other space research, to support any projects that might want to go up there for any reason. One of the other things that we're doing on there, and both of these are actually at our table out there. We have both these parts here, so we can show them to them if anyone who's interested, is we're making changes to our fins. One of the things Ryan talked about before is how we've had our titanium leading edges, and now we have core fins. We used to just have a solid composite fin, but we found that with using vented core, aluminum core, that we're seeing mass savings of up to 19% of our total fin mass. And it's really not too much different of a manufacturing process. It doesn't really take us much more time. And it's going to be super helpful on this one.
Yeah, and the main issue with that is, of course, like heating. If it gets too hot between the core and the carbon face sheet, it might want to rip apart more so than like a normal sheet of carbon. So that's why we're, again, checking all our boxes on that one, which is why we're doing a test flight.
Curious how you test or simulate that, because it's such a variable, right?
Yeah.
How are you guys testing and simulating fins?
Yeah, so we have an analysis team. They use, ANSYS. They use software as well as they do, of course, hand calculations on the side. NASA has a tool that I think is like open to the public called I don't know what it stands for. It's called FIAT. It's an ablation modeler. So for heating reasons, we include our thermal paint. We see how hot the fin's going to get. That'll tell us whether or not the carbon is past its glass transition temperature, whether or not it's likely to disbond from the core. And then on the core standpoint, we just had to get all the stiffness of everything, the strength of the adhesives we're using. It was it's a deceptively difficult problem to solve. You might think just, okay, add core to your composite, it works. But specifically, because we want to hold ourselves to like a high standard of reliability, we've done all the calculations, stuff like that.
One of the other things that we have been working on is parachute dev manufacturing. I'll talk about two different parts of this. First of all is, as some of you I know, we had a failure semi-recently for Aftershock I, and one of the things that we took away from that flight is we thought more about our recovery system. We thought more about what forces our parachutes were going to take. We then looked more back into our history and found that actually the last time that we did a space shot, the parachutes came back looking like this. So upon learning this, the recovery team had about 2 months to fix that, because now we're going even higher, right? So if those parachutes were coming back and looking like that, then there's no way that the parachutes we were going to use would survive. But they only have 2 months, right? They can't manufacture parachutes in this time. So what we did starting off is they looked at all of the failure points along that original parachute. Those are all seams that are ripped out. They went through and they strengthened all of those seams. And then they immediately started on their next project, which was saying, if the parachutes we are buying are not going to be functional for the projects, then why are we buying them? Parachutes is one of the very, very last parts of our vehicle. That's not something that we manufacture ourselves. And so they have started manufacturing them. And now we've had like 20 parachutes that we've made in-house, and we're currently doing drag testing on them, and it seems like they're gonna hold up a lot better. And then this parachute did come back a lot better.
Yeah, this is the after-flight state of the Aftershock II parachute, which they reinforced, and it performed a lot better. Mm-hmm. So on Malibu, on our next flight, we're testing now our own in-house manufactured parachutes. And then another thing we're doing for the recovery system is testing a new method of dual deployment. This is a custom pin puller system, as opposed to, we've tried line cutters and tender descender in the past, but this one is specifically light, and it kind of conforms to other parts of our system that we've kind of been using, and combines them all into one. Like, for example, this little divot right here will serve as an eye bolt, any standard eye bolt that you might tie a cord to. This pin puller also doubles as that for mass and for space reasons. So essentially just inside this chamber, E-matches will deploy this pin, shoot it out, and tied to this pin is the kind of main parachute tie-down point. So once it ejects, then that's when the main will be released, as opposed to a line cutter or a tender descender. We think this will be more reliable because we've had failures in the past actually with, I believe it was a tender descender where the line, one of these lines, there's a wire routing to it from the avionics unit actually snapped before the shock cord took all the force. The most exciting thing I think we're doing is moving towards payloads. So we're trying to essentially start serving as a research slot provider for suborbital spaceflight. This we're flying on our next vehicle in 2 weeks. You can actually see it at our table, a mock-up of it. We want to validate that we can design an aerodynamically stable return capsule, which there's a good amount of literature on it, for mostly NASA missions. We want to build the capability, to put somebody's payload within here. And of course, on this flight, we're just kind of getting data on what are the dynamics like so that we can provide that information to somebody who might want to fly on our vehicles. On the inside, it's pretty simple on this one. It'll get bigger on future vehicles. It has a run cam just for footage. It has a Blue Raven for parachute deployment as well as accelerometer data, which will provide as info on how the thing is falling. And then it has a global star for recovery. We also have a parachute and a motor sticking out here. We've tried to do, some fancy simulation on, on how stable the thing is. We're pretty confident, especially this is an old geometry. We retuned it to look a lot more like there's a NASA capsule called Stardust that flew in, I believe, 1999. We've been looking into a lot of stable geometries for something like this. And then, lastly is our hamster unit. This has been flying for maybe about 4 or 5 years, this specific architecture. We make our custom boards, we mount them on this unit, and like I was saying, we want to move towards even more reliability of the system, especially since the failure of Aftershock I, which was, at the end of the day, an unfortunate, simple user misinput. We want to not only increase our operational reliability in terms of following a precise script, double-checking everything, triple-checking everything, but we also want to build the system so that it can't fail by any one point anymore. So we have, redundant systems, telemetry links, and one important thing is we have begun using more GPS systems that send a message to a satellite and then back down to you rather than just a direct line of sight radio to you, because that might not always give you the information on where the rocket landed. And we do a lot more testing now. Prior to flight, we have a very long checklist of things to make sure of before we are good to launch, which again it's a constant struggle over the course of the club's history to learn how to be more reliable. The last super interesting thing we're flying on this rocket is called the Lightspeed Rangefinder. It's our own positioning system. We've flown it a few times in the past, although I believe only one of them, the board was fully working, because this is a custom board. It always has issues. On Aftershock II, actually, although the rest of the system was reliable, this one is considered kind of auxiliary, and it's not necessary for parachute deployment, so we decided to fly even though it wasn't working. I think it was a hardware issue, a certain solder connection came undone. But basically what it does is we have ground stations. It's just like GPS, but from the ground, 3 or 4 ground stations a few miles away from the launch point with radio transmitters. They send messages to the rocket, and then you just can calculate the time of travel for that, corroborate with the 3 ground stations after the fact, and you can calculate kind of the position of the rocket over the course of the flight. So we'll be flying that in 2 weeks. We've flown it before at the MTA, and it worked. It actually is what helped us find where the rocket landed. It's a lot greater precision than inertial systems. The idea is essentially our error bars on the altitude for Traveler 4 and for Aftershock II were pretty high in the tens of thousands of feet. This theoretically, of course, probably with the caveat, this theoretically can get up to like 100 feet of precision. Yeah. Here's some data from that. This is the Aftershock I launch. The rangefinder system was working. So we saw where the nose cone in the avionics unit fell, and it did a very good job. This is the blue line, is the rangefinder system, and the red line is what actually happened, and it seemed to work. So yeah, that's the end of our presentation. Thanks to the RRS, and yeah, we'd be happy to take any questions.
What's the launch in a couple weeks? What are you doing?
Yeah, that's this one, Malibu. So it's got the new cord fins, it's got new recovery system, the pin puller, and this payloads capsule. Those are kind of the main things we're testing out on it.
Yeah.
Well, yeah, thank you guys.
Good work.
Thanks for the presentation.
Yeah.